All right, so we're doing assignment 43. And we're going to look at problem 48. So first I'm going to read the problem. And there's a lot of verbiage there, so it's important to write down my given so I don't make a mistake and mix up values. So it says two masses, M1 and M2. So M1 is equal to 4 kilograms. And M2 is equal to 2 kilograms. They're attached to each other by a massless rod. And that's important that the rod is massless, because this way I'm not going to be concerned with the moment of inertia later on. So the fact that the rod is massless is important, but I might have a problem another time where the rod does have a mass. Okay, so that's important. They're attached to each other. The length of the rod is 2 meters. The device is on a frictionless surface. Now, what I want you to do is I want you to look at the picture of what's happening. Understanding the orientation of this picture is important. The orientation of this is I'm looking at it from above, okay? And that's important because sometimes when you're looking at a problem and there's always going to be a picture, students get confused with the orientation, and that can change a problem. All right, so that is looking at above. A third mass, and also that it's frictionless. The third mass, M3, is 4 kilograms. And it's moving at, so V3 is 10 meters per second. It collides totally inelastically with M2. So now they ask you to find a bunch of things. So first of all, it says, A, find the center of mass of the system at the instant after the collision. So I'm going to draw a picture, all right? So with my picture, before it starts to rotate, here's M1. And then over here, M2 and M3 are going to stick. So over here, I'm going to have M2, and I'm going to have plus M3. Now, the reason they want you to find the center of mass is, now when you're actually doing an FRQ, they might not tell you to find the center of mass, but whenever you have a problem where there's going to be rotation, you want to identify the pivot point, correct? The axis of rotation. So in this case, the pivot point is the axis of rotation, which why you have to find it, because we're identifying the pivot point. All right, so how do we find the center of mass? So we find the center of mass that XCM is the summation of all the masses times the distance to the axis of rotation all over the total mass. Now, when I was taught how to do this back in the day, we always used as our frame of reference the left. Kind of like when you do the origin of a graph. So that is our frame of reference. So now when I want to find the center of mass, it's going to be this mass, M1, which is 4 kilograms, times the distance to my frame of reference, which here it's going to be what? 0. Plus this total mass, M2 plus M3, which is going to be 2 plus 4, times this distance to this frame of reference. So that distance there is 2 meters. Divided by the total mass. So the total mass is the 4 plus the 2 plus 4. So my XCM, and this is part A, is going to be 12 divided by 10, which is going to be 1.2 meters. So this is kilogram meter divided by kilogram. So we end up with meters. Now remember, I'm measuring from here, so because I know this total is 2, I know that here, 1.2, this is going to be my center of mass. And that's going to be, and then this would be 0.8. So once this object starts to rotate, it's going to rotate this way. And it's going to rotate this way. Because remember, the first one hit here, And then this is going to be the pivot point that it's going to rotate, right? So that's why we found the center of mass, all right? Part B says the moment of inertia of the system. So again, we identified the direction that it's rotating, and we see that it's rotating counterclockwise. So you always want to identify where it's going to rotate in what direction. So now we can go on and do part B. Well, the moment of inertia, these are point masses, is just going to be mr squared. So it's going to be 4 kilograms times 1.2 meters squared plus 2 plus 4 times 0.8 meters squared. Remember, I'm doing the mass times the distance to the axis of rotation. So this comes out to be 9.6 kilogram meter squared. Part C says, the total angular momentum of the system about the new center of mass. So remember, we learned two things. We learned L is equal to I omega, and we learned L is equal to mvr. So the easiest way is, remember, angular momentum is conserved. So the total angular momentum before is going to be equal to what? The total angular momentum after. So what we'll do is we'll do L is equal to mvr. So we'll say m3 v3 r3. So this is going to be equal to 4 kilograms times 10 meters per second times 0.8 meters. So this comes out to be 32, and we have kilogram meter per second times a meter. So my final unit is 32 kilogram meter squared over a second for my angular momentum. Now, part D says find the angular velocity of the system after the collision. So that means I want to find omega f. Now remember, if I use conservation of angular momentum says the total angular momentum before is equal to the total angular momentum after. Now remember, on AP questions, whatever answer I found for A, I'm going to use for B. Whatever I found for B, I'm going to use for C. And pretty much, it's going to go step by step. So conservation of angular momentum basically says L naught is equal to LF. The total angular momentum before is equal to the total angular momentum after. Now, we found this was mvr, but I already found this in the previous section. Now, the total angular momentum after is going to be I omega f. Now, remember, we found I in part B. And now we found this in part C. So for part D, we're just going to rearrange that, and we're going to find omega f. So omega f is equal to L naught divided by I. So it's equal to 32 kilogram meter squared per second divided by 9.6 kilograms per meter squared. And this comes out to be 3.33 radians per second. So this is conservation of angular momentum. The total angular, when we do gravitation in the next unit, when we have planets going around the sun, angular momentum is going to be conserved in our elliptical orbits as well. All right. Now, here's an interesting thing for part E. It says find the linear speed of the mass after the collision. Well, the linear speed in part F, the tangential velocity of m1, end up having to be the same thing. Now, let's pretend we didn't read part F, because obviously we would just say, like, V is equal to R omega, and that would be easy. But let's look at What if we did conservation of linear momentum to find this? So the whole point of this is to see that our answers are the same. So if we did conservation of linear momentum, P naught is equal to PF, we would end up with M1 plus M2 times V naught plus M3 times V naught would be M1 plus M2 plus M3 times V prime. So if I substitute in my values 4 plus 2 times 0 plus 4 times 10, that equals to 4 plus 2 plus 4 times V prime. And when I do all that, I see that V prime ends up being 4 meters per second. In part F, it says find the tangential velocity, where, well, the tangential velocity V is equal to r omega. So that's going to be 1.2 times 3.333, which I got up there. And I see that also comes out to be 4 meters per second. And now part G. So part G says, what is the total kinetic energy? Well, this object is rotating and translating. Well, I have both rotational and translational kinetic energy. Okay, so that's why we have to find the sum. So the total kinetic energy is going to be 1/2 I omega F squared plus 1/2 mVF squared. And you see we're using all the other stuff that we had calculated earlier, and that's typical. So now I'm going to substitute in my values 1/2 of 9.6 times 3.33 squared plus 1/2, and then this is the mass of all three, remember? So this is going to be M1 plus M2 plus M3, so that's going to be 10 kilograms times 4 meters per second squared. So the total kinetic energy comes out to be 133.2 joules. So there's a lot of parts to this, and this is typical of the type of a question that you would have on an AP exam where they're going to ask you all the little intermediate parts. So again, when you're doing this problem, you're going to say to yourself, where's the center of mass of the system? Because the center of mass is going to tell me, you know, the pivot point of where it's going to rotate. Then I'm going to say, what is the sign convention and what direction is it rotating? And then again, step by step. So when we're using conservation of angular momentum, remember, not only is it I omega, it's also MVR. All right. And then again, step by step. That's it.